we find in many physical situations the weight of a body changing. We talk of some real weight and apparent weight. This famous elevator lift example, once again made very, very famous by the great person Einstein. We'll discuss this one to see how the weight we defined previously as the force by which a body is attracted to be changing in various situations. Here we are looking at this person. This person is standing in a stationary lift, and when he's standing in a stationary lift, we say that his weight is some 800 newtons, and we say it is real weight. Probably the lift is stationary, it is equivalent to standing on a weighing scale on the earth's surface. So we said his weight is 800 newtons. That may be like this: m equals 80 kilograms and g equals 10. So the product is F equals mg, that is 80 into 80 kilograms into 10 newton per kg, the value of g. So the weight is 800 newtons. But now when this person is accelerating like this, he reads a different weight. On the weighing machine, he'll read different weights. For example, if this lift is going up with an acceleration 2 meters per second square, how does this lift go with an acceleration 2 meters per second square? Probably the force, the tension in the cable and the weight of the lift plus person together may be producing an acceleration 2 meters per second square upwards. Now, of course, we are not interested in what's happening to the lift plus person as a whole. We are just looking at the person here whose weight is now appearing to be different. And he reads, it seems, greater weight if the lift is accelerating up. For that, we are given formulas like this. W apparent is equal to W real plus 1 plus A by G is a formula given when the lift is accelerating up. So here take the values, 800 newtons here we have, and 2 we are substituting, and G once again for the sake of calculation purpose we'll make it 10 instead of 9.8, 800 into 1.2, and that will be becoming 960 newtons, which is greater than the weight when he is at rest. Or supposing the same lift is coming down with the same acceleration downwards with A equals 2 meters per second square, another formula is given, and that formula says W real into 1 minus A by G is the apparent weight of the person, and once again substitute, you'll get 640 newtons, which is less than the true weight we call. People say it's a true weight, real weight, less than this 800 newtons. Or if the lift is supposedly falling down with A equals G, that means if it is coming down with 10 meters per second square, and this apparent weight from the formula appears to be 0. So when this kind of a discussion is done, of course, people try with various methods here which are not very appropriate. I'll be discussing the correct approach anyway later. But the very fact that you define weight as a force by the earth, and that is m into g, now suddenly because of this motion the weight is changing. That's somewhat confusing for the children first, because his mass will be same. 80 kg means 80 kg, nothing will go out of his body, and g at this place will remain same. Of course, don't worry about the change of g because of this small height it is going through, because change in the weight because of the acceleration is much higher than what you compared with the change of g on the distance. So g is almost constant, we can say. So why this weight, the reading is actually becoming different. The weight reading here shown is why it is less 640 or why it is more there, and what do you mean by that becoming 0? Because it's still standing there, and this machine shows nothing, as if the acceleration told the machine that come on, don't show any weight. So this we need to address in a proper way. Actually, this explanation of this thing comes properly from, as I told you, the Einstein's principle of equivalence, which I'll be discussing sometime later. I don't want to mix it up with this. I told you our idea is to understand this within this F equals ma and F equals g mm by r square. Yeah, we'll go to another example. The weight of a stone, for example, weight of a body is measured in air. Here it is hung from a spring balance, and you might take, for the sake of numbers, that weight in air is some 500 grams. That means this spring balance is showing some 500 grams weight it is showing. Now we take this stone and submerge it in water, and suddenly you appear the weight to decrease, the reading to decrease here, and we'll say W water is 350 grams. And once again the weight is changing, and we say when a body is submerged in a fluid, in water for example, here it loses weight, and we give explanation for that from Archimedes principle. But once again that idea is going to bother. People say, of course, the force of buoyancy pushes it up, therefore the weight decreases. Remember, for the weight to decrease, as I've talked, since that is F equals W equals mg, either m should change or g should change. None of it is changing here. Neither m is changing. Look, the stone is remaining as it is, and g at this place on the ground should not change, because r of this is not changing from the center of the earth. Therefore, once again mg should remain from the definition, the way we defined it. But the experiment shows this spring balance says no, once you put it in water I'll show less weight. So that will be slightly disturbing actually. Not really. We'll go for more examples and talk about it again. This is all the time we keep seeing in the scientific fiction movies, or some real videos are all available all over the internet. The astronauts here are floating. They are in zero gravity situation, people say. Isn't it so? And their weight is zero, people say. But once again, it's not very clear. You know, when a satellite is going around the earth, the force which is a reason for this satellite to go around is nothing but the gravitational force. Now you may call it mg, the weight of it, or you might call it m into gm by r square. This force is the reason for the satellite's motion in a circular path. Isn't it so? Like we fire a satellite using rockets, it goes there, after going there we'll give it a horizontal velocity, enough horizontal velocity, then it becomes a satellite. And supposing suddenly something happened and this mg or gm by r square disappeared, the satellite will just go along the tangent. Right? That means the satellite is under the effect of gravity. That's the gravity is the only one which is actually making it go in a circular path around the earth. If the satellite is going because of gravity, or gravity is making the satellite go in a circular path, even the persons are going along with the satellite because of gravity on them. Isn't it so? So saying that their weight is zero is definitely somewhat perplexing for a student in school. Even this we need to address. And there's one more example we'll discuss here. The weight of an object near the equator is less compared to its weight on the poles. And people say this GE is becoming less because of the rotation. That's why the weight is here less, the weight is here more. Once again the same problem we face. Why G is changing? Because G is gm by r square, like r is same here and here, there. Supposing it is a perfect sphere. The reason they say G is decreasing here is because of rotation, not because of R anyway. So neither capital M, that is mass of the earth, is changing, nor the distance is changing, but still G is changing. And once again, some kind of explanations are offered, which are half correct and half wrong. We'll now go to understand two things about weight. One is, apart from the definition we mentioned, that weight is the force applied by the earth on the object. How this weight has come into our usage, the word weight has come into our usage, is very, very important. That is, our feeling of weight, our feeling of heaviness is actually made us introduce the word called weight. Every day people nowadays are worried about their weights going up because of lack of exercise. Now, that's what I mean by the feeling of weight. Feeling of heaviness we need to understand. And then second thing is, how do we measure weight? Once this is done, we can actually reconcile many apparently opposing aspects of weight in a proper way. Look, this person is standing on the table for whatever reason, and he feels, of course, heavier. He feels heavy, actually, let me say, not heavier anyway. He feels that he's got some weight when he's standing on the table, because if somebody comes and removes this table, he'll be falling down to the ground. During this fall, he wouldn't feel any weight. Once he touches once again this ground, once again he thinks he has got weight. But before I discuss this thing, I'll just come to one more misconception people have about this other force called N. I'll just now show it. Now this person applies mg on the table, and this is the action, and this table applies N on him, which is called the reaction, the normal reaction to the weight. Is it correct? Yes, some of you must have already noticed whatever I told is not correct. This is the one I want to really clear first, because the whole idea of weight is not weight measurement, but it is measurement of that N and some other forces. Now, it is like this. I'll come back again correctly. Weight of the person is still that force with which earth is attracting the person. I'll put earth here. This earth is attracting the person with m into g. And in turn, the person attracts the earth with the same mg. And this mg can be termed as action of the person on the earth. And this is the reaction of the earth. Reaction of earth on the person. And remember, this mg is acting on the ground, that mg is acting on the person. There's nothing like they cancelling. Okay? Cancelling on whom? It cancels neither on earth nor on the person. But now, since this person is pressing the table, his feet are pressing the table. So the molecules of the table and molecules in the feet of his molecules in his feet, they are trying to compress into each other. They are actually trying to come closer than their equilibrium distances. Therefore, they start repelling. The molecules repel. Like if you press your two palms very hard, you feel that pressure away like that. The table molecules of the table and molecules in his feet will be pressing each other, and they develop a repulsive force. So that is what you call as N. We call here N. We talk about. So this person presses the table hard like this. You can call it N. this is normal to the surface, therefore n, and the table in turn pushes him back with n. So this n is what is the action of the person. This is action of the person on the table, and this n is the reaction of table on the person. So when I just simply separate this fellow out, take him out somewhere here and show, this is what you mean by the isolation diagram approach. There's a reaction called weight by the ground. There's a reaction called n by the table. These two reactions, remember I told you F equals ma is, left hand side F is the sum of all the reactions, right hand side is mass into acceleration. Mass of this person is m if I say, and his acceleration is 0 because he's not moving. So we'll write n plus n, probably upwards plus I can put, downward minus I can put, equals 0, n equals mg. So this has to be clearly understood. What I'm trying to tell you is this: when a person stands on a surface, he will develop one molecular force, or this force is basically electrical in nature. That force develops, and when you push an object, you are trying to push the molecules into objects closer. They repel each other and develop a force called contact force, I can say in general, but this contact force being normal to the surface, we call it normal contact force. But this will be once again an action and reaction business. You apply n on the table, table applies n on you. And because of this, and this accidentally here, it so happened n is equal to mg. So that you feel that you got a weight because this n is making you feel that mg. Right? That's one thing. Now measuring weight. Yeah, this person says, oh, my weight has increased. Right? But why? How do you measure this weight? Just now I explained all that. This n which he applies on the weighing machine is the one which is actually showing the reading. Because when he applies n on that spring mechanism inside, that will compress, for example, spring mechanism or whatever mechanism inside is compressed, and that develops a force against holding him. That is called some kind of a compression force. That is the one which is actually showing a reading here. Whatever, for example, his weight is some 1000 newtons. That is 100 kilograms in the popular usage. So 1000 newtons weight it shows. It is actually the reading of this n, which is of course, is mg is anyway acting down like this. The same n is acting upwards on him. So that n minus mg equals 0 we make. And since n is shown to be 1000 newtons here, his weight is 1000 newtons. So this is the idea of measuring weight. What we need to understand is that we develop one opposing force to the so-called weight and measure it.